Good day, everyone. Today, I'm going to discuss another soil physical property, which is the soil structure. So, let's begin. When we talk about the soil structure, it refers to the arrangement of primary particles into secondary particles, units, or beds. So, if you can remember on our discussion about soil texture, the primary particles are composed of the sand, the silt, and the clay. And when those primary particles form aggregates or form into secondary particles, units or beds, that is when the soil structure is being developed. According to the Soil Science Society of America, there are six types of soil structure. So this is the table according to them. So one is the structure that is called granular. Granular resembles cookie crumbs and is usually less than 0.5 centimeters in diameter. This kind of structure is commonly found in surface horizons. When you say surface horizons, it could be O and A horizon or any of the two, where roots have been growing. Another one is the blocky, which includes irregular blocks that are usually 1.5 to 5 centimeters in diameter. So it is usually larger than the granular structure. So aside from the granular and the blocky, we have the prism-like, such as the prismatic and the columnar. Now for the prismatic one, prismatic includes vertical columns of soil that might be a number of centimeters long. This kind of structure is usually found in lower horizons, maybe in the E or the B horizon. And how about for the columnar? Columnar is very similar. The only difference is that columnar structure have a salt cap at the top. And this one is commonly found in soils of the arid climates because soils of the arid climates are prone to salinization. And we also have the platy structure, which is composed of thin, flat plates of the soil that lie horizontally, usually found in compacted soil. Another is the single grain. This one actually could be called structureless. In the soil structure, the soil is broken into individual particles and do not stick together. And it always accompanies a loose consistence. This kind of structure is commonly found in sandy soil. The soil structure or the amount of aggregation is easily changed in the way soils manage. So unlike soil texture cannot be easily changed, while soil structure can be easily changed in the way the soil is managed. For example, tillage operations tend to destroy structure, while addition and decomposition of organic matter, lime, and other binding agents like the iron and aluminum oxides, clays, and silica tend to build up structure and promote soil aggregation and aggregate stability. So, soil management could either destroy or could build or could develop aggregation or aggregate stability. Now, in understanding the soil structure, you must be familiar with the difference between soil aggregate and the bed. When you say soil aggregate, it refers to many soil particles held in single mass or cluster, such as the clod, the crumb, the block, or the prism. While bed, when you say bed, it is a unit of soil structure, such as an aggregate, crumb, prism, block, or granule formed by natural processes. So that's the difference between the two. Now, soil structure is being classified based on the shape of the beds, such as spheroidal, platy or plate-like, prismatic, block-like, single grain, and massive. So let's discuss this one by one. Now, for the first soil structure, we call it spheroidal. Spheroidal soil structure is either granular, which is porous and may be separated from each other in a loosely packed arrangement, or it can be crumb, which is very porous. This soil structure contains aggregates that are not over a half inch in diameter. And this is the only type of aggregation commonly found in the A horizon, which are influenced by the practical methods of soil management. So if you remember on the different types of soil structure according to the Soil Science Society of America, the granular one is commonly found, or the granular structure of soils are commonly found in the upper or surface horizons. Now, for platy or plate-like structures, these are characterized by relatively thin horizontal beds or plates, which are often inherited from the parent materials, especially those laid down by water or ice. These structures are most noticeable in the surface layers of virgin soils and commonly found in e-horizons, but may characterize the subsoil horizons as well. For the prism-like structure, as what I've said earlier, it can either be prismatic or columnar. For prismatic, it contains or it has a structure wherein the tops of the prisms are relatively angular and flat horizontally, while in columnar, the pillars have distinct rounded tops or salt cap, and this kind of soil structure is commonly found in the subsoils of the arid and semi-arid regions. And when well developed, it is a very striking feature of the soil profile. So these are some examples of prismatic and columnar soil structures. So you can easily notice the difference. For block-like, these are either angular blocky, in which the edges of the blocks are sharp and the rectangular faces are distinct, or it could be subangular blocky, in which the corners are mostly rounded. So there is subrounding that has occurred. And these structures are usually confined to the subsoil or the B horizon state of development. And other characteristics have much to do with soil drainage, aeration, and root penetration. So another soil structure is the single grain, so the one we have or I have mentioned earlier. So the single grain structure contains particles that show little or no tendency to adhere to each other, and it is often associated with very coarse soils or very coarse particles such as the sandy soils, and this is commonly found in very young soils. For the last one, we have the massive soil structure. So this soil structure shows little or no tendency to break because it is very massive, very compacted. There is no tendency to break apart under light pressure into smaller units, and this one is often associated with very fine textured soils, such as the clay soils. So now when we talk about soil structures being formed, or how do aggregates form? Now, the formation of soil aggregates are affected by several biological, physical, and chemical processes. So let's discuss those processes one by one. For the physical chemical processes, this includes the flocculation, or the mutual attraction among clay and organic molecules. This one also includes the adsorption of cations, either polyvalent or monovalent, and volume changes in clay materials through the swelling and shrinking of the soil resulting from either wetting or drying, or freezing and thawing. So let's discuss these physical chemical processes. For the flocculation of clays, it involves the mutual attraction among clay and the organic molecules, which begins with the flocculation of clay particles into microscopic clumps, or floccules. We also have the adsorption of cations, either polyvalent or monovalent. For polyvalent cations, examples are the calcium, iron, and aluminum ions. So these polyvalent cations can effectively neutralize the negative surface charges on clay particles. And this kind of cations can form bridges that bring clay particles together. So polyvalent cations can stick together clay particles. When you compare these polyvalent cations with monovalent cations, especially the sodium ions, these monovalent cations can cause clay particles to repel to each other and create a dispersed condition. So meaning to say, polyvalent cations cause flocculation of soil particles, while monovalent ions, or monovalent cations, especially the sodium ions, causes dispersion of the soil. For the volume changes in clay materials, so as the soil dries out, soil mass shrinks and cracks will open up along zones of the weakness. Now, that is because of the shrinking and swelling. Swelling and shrinking actions that accompany freeze, thaw, and wet dry cycles in soils create fissures and pressures, breaking apart large soil masses and compressing soil particles into defined structural beds. So over the course of many cycles, so this process what? Create defined structural beds that can create network of cracks that can become defined at the long term, in the long run. Now, for the biological processes, basically it um, involves the works or the activities of the soil organisms. And the most prominent biological processes of aggregation are the following. So first, we have the burrowing and the molding activities of soil animals, the enmeshment or mixture of particles by sticky networks of roots and fungal hyphae, and the production of organic glues by microorganisms such as the bacteria and the fungi. Aside from that, other activities would include the earthworms and the termites' movement in the soil. As these soil animals move, they can also move soil particles. Another is through the plant root movements. No, plant roots move particles as they push their way through the soil. So this forces soil particles to come into close contact with each other, therefore encouraging aggregation. Now, channels created by the plant roots and the soil animals can serve as large pores, breaking up clogs, helping to define large structural units of the soil. The plant roots and fungal hyphae exude sugar-like polysaccharides, and other organic compounds. So these polysaccharides or sugar-like polysaccharides and other organic compounds can form sticky networks that bind together soil particles and microaggregates into macroaggregates. The thread-like fungi that associate with plant roots, so what we call the mycorrhizae, can also produce glomalin. Glomalin is a sticky sugar protein which can act as a cementing agent. Another is that bacteria could produce polysaccharides and other organic glues as they decompose plant residues. Now let's talk about some of the factors that can influence the soil structure or aggregate formation. So first we talk about the influence of organic matter. Now when you say organic matter provides the energy substrate that makes possible for biological activities to occur. During the aggregation process, soil mineral particles become coated and encrusted with bits of decomposed plant residue and other organic materials. The complex organic polymers resulting from decay chemically interact with particles of silicate clays and iron and aluminum oxides, and these compounds help orient the clay into packets, which form bridges between individuals of particles, binding them together in water-stable aggregates. Another factor that can influence soil structure aside from organic matter is the tillage. Tillage can both promote and destroy aggregation. For example, if the soil is not too wet or not too dry, tillage can break large clods into natural aggregates. Therefore, the soil will become loose, will become porous, and that's the time it will be conducive to root growth and seedling emergence. And while performing the tillage, you can also incorporate organic amendments into the soil and kill weeds. However, over a long period, tillage can hasten the loss of organic matter. Therefore, when organic matter is lost, it can promote the weakening of the soil aggregates. So there would be lesser or no more cementing agent. Tillage operations also tend to crush or smear soil aggregates. This might lead to loss of the macropores or porosity of the soil. Now we move to the effect or the influence of iron and aluminum oxides in soil structures. So these sesqui oxides coat soil particles and cement soil aggregates, thus preventing their ready breakdown when the soil is tilled. Now the cementing action of the iron oxides and other inorganic compounds produces a very stable small aggregates called the pseudosand. Now, in using the soil for agriculture or buildings, constructions, and many other uses, it is important that the soil has a stable aggregation. And when you say aggregate stability, it refers to the ability of the soil aggregates to resist disruption when outside forces, usually associated with water, are applied. Now, why aggregate stability is important? Because it affects erosion. It affects the movement of water. It can also affect plant root growth. Now, we need desirable aggregates. And when you say desirable aggregates, it means that the aggregates are stable against rainfall and water movement. Because aggregates that break down in water could release individual soil particles, and those individual soil particles can seal the soil surface and clog pores. It can lead to flooding, it can lead to waterlogging, and we don't like that. So for plant growth, the optimum is that the soil has a large range of pore size distribution. which means that it should have large pores between aggregates and small pores within aggregates. Now, the pore spaces provide zones of weakness and through which the plant roots can grow. Because if there are no pore spaces, there would be no place for the plant roots to grow or to extend. Now, there are management practices that can improve the soil structure for plant growth, such as this one, the organic matter management. Regular additions of organic matter feed organisms that build the soil structure. Residues left at the surface of the soil protect aggregates from rain and encourages the growth of fungi that can help stabilize the aggregates. Another is through compaction prevention or via cropping. Tillage and organic matter addition can prevent compaction. Why do we need to prevent compaction? Because compaction pushes aggregates together and eventually breaks them down. For cropping or cropping system, the dense roots of grasses, small grains, and pastures can stabilize soil aggregates. Therefore, it can improve the soil structure. So that's all for our discussion about soil structure. Thank you very much for watching. Please like and subscribe.